The Intergovernmental Panel on Climate Change, the IPCC, was chartered in 1988 to do research into the climate and to see if increasing levels of carbon dioxide were affecting the climate. Since then, the IPCC has expanded its research efforts, issuing reports every 6 years. The research depends on climate models that capture the physical dynamics of the Earth's atmosphere. Over the years, more models were developed to assess additional factors that affect the climate. The premise of the models is that the climate is controlled by the atmosphere. Therefore, modeling the atmosphere would reveal how changes affect the climate and, from that, Earth's temperature. In 2013, the IPCC issued a fifth assessment report. It published groundbreaking results. IPCC members were satisfied that there was a sufficient span of time, 60 years, and enough data sets across those years to identify with confidence the actual rate of warming. The 1990 report predicted a rise of 1.2 to 3 degrees Celsius over 6 decades. The 2013 reported the actual warming was 0.64 degrees, or about 0.1 per decade. The fifth assessment also reported the warming from 1850 to 2010, 0.85 degrees, or about 0.05 per decade. After years of dedicated and expensive research, why are climate models unable to reproduce the actual warming? On the premise that the climate is controlled by the atmosphere, the IPCC needed a conceptual basis for constructing its models. The IPCC adopted a century-old idea, the theory of the greenhouse effect. Climate researchers developed an approach, the radiative forcing concept, to explain the greenhouse effect and to serve as the architecture for climate models. The models attempt to replicate the physics and thermodynamics of the atmosphere to see how heat and energy move through it, and to see how an increase in the amount of carbon dioxide might influence the climate. Energy comes in many forms. We were taught in school that two forms are potential energy and kinetic energy, sometimes also described as stored energy and energy from motion. As this graphic illustrates, energy comes in other forms. For example, chemical energy, which is the energy we use to carry the anvil up a flight of stairs. Energy sometimes moves in mysterious ways. Magnet energy, for instance, which can move objects without exchanging any heat energy. Energy can be stored in atoms, such as uranium's internal energy, ready to be unleashed via nuclear fission. As to the climate, we are particularly interested in two forms, thermal energy and radiation energy. We'll start with thermal energy. We're very familiar with it. We heat homes with it, cook with it, and sometimes swelter in it. It is dependent on the temperature of matter, be it gases, liquids, or solids, and can be measured with a thermometer. Thermal energy comes from the sun, the atmosphere, and the Earth's surface. Starting with the sun, we'll ask a question. Why does its energy warm the Earth? Radiation from the sun travels through space. It doesn't warm up anything on the way. When the radiation reaches Earth, a significant percentage, 30%, is reflected back into space. The atmosphere and clouds absorb 19%, and the Earth's surface absorbs 51%. Sunlight is a spectrum of radiation, shown by the yellow curve on the inset graphic. It is mostly short-wavelength, high-energy radiation, including ultraviolet, visible light, and infrared. By day, the sun generates thermal energy. It heats things up at different rates. Rocks and deserts warm more than water, for example. The tropics, directly under the sun, warm up more than northern latitudes. Layers of the atmosphere also warm at different rates. This uneven warming results in temperature differences that cause heat energy to move. And thermodynamics tells us that heat, or thermal energy, can only go from warm to cold. It cannot go the other way. Thermal energy is transferred by conduction, direct transfer from one molecule to another, or by convection, the movement of fluids. Bodies of air move and take heat energy with them. Warm air rises and cooler air sinks, creating vertical air currents like the thermals used by gliders. This is sensible heat. Water vapor moves heat by rising into the atmosphere to condense into clouds. Liquid water moves heat by evaporating from the ocean or ground moisture. The heat associated with water changing phase from liquid to vapor, or vice versa, is latent heat. This heat is transferred with no change in temperature. Air and water vapor also move heat energy across the atmosphere and around the globe, creating weather patterns and trade winds, for example. Liquid seawater moves heat in the form of ocean currents. For example, the Gulf Stream causes Iceland to have a temperate climate even though it borders on the Arctic Circle. Thermodynamics apply to systems that contain solids, liquids, and gases. The lower atmosphere is such a system. Compared to the Earth's diameter, it is a very thin layer. And about 75% of all atmospheric gases are in the lowest 10 kilometers. In this region, the red plot shows how the temperature changes with altitude. It drops steadily from the surface up to 10 kilometers, and above that, amazingly, the atmosphere becomes warmer. When matter becomes undense, when molecules and atoms aren't packed closely together, temperature takes on an alien nature from our perspective. It becomes more a reflection of molecular energy flow, not a measure of thermal energy flow. Energy is flowing, it's just not the temperature energy we feel and experience on Earth. This is particularly the case above 35 kilometers where the air is very thin. To recap, thermal energy is heat that moves from warm to cold, primarily by convection. It involves sensible heat, like when a warm gas cools down and changes temperature. It can be latent heat, as when water vapor condenses into water droplets and heat is transferred during the phase change without a change in temperature. Finally, thermal energy is driven by the different temperatures across the Earth's surface or vertically in the atmosphere. Radiation energy in the atmosphere is very different. We know that radiation comes from the sun, but radiation is also generated by matter. Radiation comes from the gases in the atmosphere and goes both up and down. The Earth's surface generates radiation that goes into the atmosphere. Both continue to generate radiation during the night. Radiation is electromagnetic energy, commonly called electromagnetic waves. It is energy that moves at the speed of light. Radiation is not heat transfer. It is an energy transfer that may generate heat. This is very important. It's also difficult to accept. After all, we've been taught that one of three transfer modes is radiant heat, and we know it exists because we feel it when sitting around a campfire. To accept this idea, we need to decipher radiation as best we can. Radiation is not intuitive. Since mankind's earliest days, it has not been part of human understanding. Civilizations and cultures developed and evolved totally ignorant of radiation, resulting in mistaken explanations for the nature of things. It wasn't discovered until the end of the 19th century. Radiation is mysterious. Take your microwave oven, whose principle was discovered by accident. It generates electromagnetic waves that are absorbed by water molecules. This excites the molecules, causing them to collide more frequently, which raises the water's temperature. But the same radiation passes through microwave-safe plastic, and it doesn't heat the oven's interior. We can't see most radiation, another reason it's not intuitive, but we can gain insight into its phenomenal nature by examining the radiation we can see. Visible light. Picture a football stadium on a very dark night. It has only one source of light, a single bulb on the 50-yard line. If we were holding an eye chart, it would be easy to read right next to the bulb. As we walk away, it becomes more difficult to read. Up in the stands, it's probably too dark to see it at all. Radiation spreads spherically. The energy diminishes rapidly, a function of the distance squared. Covering the bulb with a red glass bowl, the light turns red. The glass absorbs most of the spectrum, but is transparent to red. Putting a steel bucket over the bulb, the light disappears. The bulb is still generating light inside the bucket, but the metal completely absorbs it. If we move the light bulb to the goal line and set a large mirror on the 30-yard line, behind the mirror there is a shadow, but not total darkness. Light reflected from stadium surfaces enters the shaded area. And if we stand at the far edge of the end zone, we would see the light bulb and its reflection in the mirror. Does this now mean that we see more light? In a way. Does this mean that the light bulb is producing more light? No, of course not. Radiation is absorbed, reflected, and scattered, entirely dependent on the material it interacts with. It spreads spherically from its emitter, carrying less and less energy with distance. Portions of the electromagnetic radiation spectrum are given labels for convenience. Infrared radiation has longer wavelengths and lower frequencies than visible light. We further break down the infrared spectrum as long-wave IR or short-wave IR. Radiation interacts with matter in many ways. The ways weren't predicted, they were discovered. Trying to explain them still drives physicists crazy. Physicists and engineers simply accept as a fact of life that each radiation interaction is a mysterious, uncertain event. Each is a phenomenon, entirely dependent on the energy and wavelength of the radiation and the characteristics of the molecules and atoms it interacts with. Together, in the plural, they are treated as phenomena. Radiation has to come from something. We saw some of the phenomena when radiation interacts with matter. Not surprisingly, its generation has its own mysteries. For many objects, the intensity and spectrum of the emitted radiation is a function of its temperature. The radiation emitted by objects known as black bodies is delivered as a smooth spectrum. These curves represent the radiation spectrum from such objects at a given temperature. The yellow curve is the spectrum of the temperature of the Sun, 5777 degrees Kelvin. The red curve is the spectrum from a black body, like a solid black steel ball, at 300 Kelvin, or about 80 degrees Fahrenheit. Most of the smooth spectrum at this temperature is emitted in the long-wave IR range. There are few black bodies in the real world. Different kinds of matter emit very different spectrums. Helium, for example, exhibits this spectrum. Different mixes of materials or components exhibit their own unique spectrums. A halide bulb creates one different from a fluorescent bulb. Said to transmit at a frequency, a cell phone actually emits a spectrum. Firefighters use radiation detectors to locate a fire's location because house fires have a unique spectrum. Even in that microwave oven at 2.45 gigahertz, its magnetron has actually generated a jagged energy spectrum. Our eyes don't see infrared energy, but we can see it with scanners. We see the unique spectrum from each of the bodies in this group. The Earth, seen from space, is not a black body. It generates a spectrum of its own. Two different spectrums, actually. One is from reflected sunlight, another from the Earth and atmosphere. Nor is the Earth's spectrum constant. A satellite above the ocean sees one spectrum, and a different one above the Rocky Mountains. When satellites measure wide areas, we see one spectrum from the tropics and another from mid-latitudes in the winter. Climate models focus on two forms of energy, thermal and radiation. Next, we'll examine how these energy forms flow in the Earth's thermodynamics system, its climate. This graphic is typical of those used to represent the energy flows. It assigns percentages on the basis of the solar energy arriving at the top of the Earth's atmosphere. 30% of solar radiation is reflected back into space, leaving 70% that is absorbed by the Earth's atmosphere and surface. For what follows, it helps to apply a new percentage basis, absorbed solar energy, what was the 70% in the previous graphic. On this new basis, the budget shows that 23% is absorbed by the atmosphere, 4% by clouds, and 73% by the surface, which adds up to the new 100%. The graphic reveals that 92% of the Earth's long-wave IR radiation comes from the atmosphere and 8% directly from the Earth's surface. Energy moving within the atmosphere is complicated. It is in three forms, if you will. One is energy generated by solar heating of the atmosphere, here labeled atmosphere heat and highlighted in yellow. The second is the heat of convection generated by surface heating. It is the combined latent and sensible heat carried by air and water vapor, marked in light blue. The third is infrared radiation coming from the Earth's surface, also in light blue. Adding them, we remain at 100%. But then we see something quite miraculous. The three forms of energy are transformed. All the energy sent out into space is infrared radiation. Putting it very simply, the atmosphere is absorbing heat and infrared radiation, and converting all of it to infrared radiation. This is phenomenal, and it takes a while, as they say, to wrap your head around this. Years ago, this amazing nature of our Earth and its atmosphere was speculation. Now, from satellites in space, instruments can measure the Earth's radiation signature. The atmosphere is phenomenal. Its mixture of gases, water droplets, and other matter interact with radiation in phenomenal ways. Some is driven by phenomena unique to individual atoms or molecules. Some is driven by the fact that they are all mixed together. And perhaps some is driven by other things that theoretical physicists may yet discover. How do climatologists explain this? And more importantly, how do they model this? Molecules interact with radiation, and molecules produce radiation, all part of the phenomena. Oxygen, nitrogen, and argon are the dominant gases in the atmosphere. I'll call water vapor a mixing gas. CO2 is a minor part of the mix at 0.04%. And finally, there are the trace gases listed here. Here's one phenomenon. The gases which make up all but a minute fraction of the atmosphere don't react to long-wave IR radiation. The waves simply pass through them or by them, unimpeded, undisturbed. This is not the case for the mixing and trace gases. They interact with long-wave IR radiation. It's just another set of phenomena. Water vapor is the gesture in atmospheric phenomena. Its influence is, well, phenomenal. Water vapor varies with latitude as a percent of atmospheric gases. We see the variability here. Vertically, water vapor is even more influential. In humid Hawaii, it is 3 to 4% of the air close to the surface. Above that, up to 10 kilometers, it hovers around 0.1%, and then above 15 kilometers, it is negligible. These graphs are actually 4 different graphs stacked on top of one another. On the left is a scale of percent of absorption for each graph. Along the bottom is a wavelength scale that is shared by the graph. We see in red the phenomenon that ozone absorbs nearly 100% of incoming ultraviolet radiation. What this means physically is that the ozone molecules absorb the sun's ultraviolet spectrum and very little of it reaches Earth's surface. In green, we see that CO2 has close to 100% absorption at specific radiation wavelengths. In other bands, absorption is at some other percentage. And we see that at most wavelengths, there is zero absorption. Water vapor absorbs in many bands, with some at varying percentages, some at 100%. Some phenomena overlap, so to speak. At wavelengths of 2.2 microns, for example, both water vapor and CO2 absorb 100%. During the day, long-wave IR radiation is generated by both the sun and the Earth. At night, of course, it comes only from the Earth. These graphs show how radiation is absorbed, but they don't give any clue as to what happens after absorption. Is the energy converted to thermal energy, like what happens to water in a microwave oven? Actually, much of it is re-emitted almost instantly at the same or slightly different wavelength, only to be reabsorbed after reaching another absorbing gas molecule, if it finds one before escaping into space. Some of the absorbed energy is transferred to nearby molecules in other forms. Some may be converted to chemical energy, or even to electricity. In fact, no one knows how much of the absorbed energy becomes some other form of energy. All we know is that eventually the energy sent into outer space is all radiation energy. Still, climate scientists think they understand atmospheric physics well enough to express them in a model. The IPCC adopted a basis developed in the 70s and 80s, the radiative forcing concept. It is frequently illustrated like this, suggesting that the atmosphere reflects or traps heat. As recently as 2007, the IPCC reported that the theory of radiative forcing remained the theoretical basis for its models. Radiative forcing assumes a balance between incoming and outgoing radiation energy. It may be helpful to outline a simplistic energy budget for the Earth as a guide to general understanding, but it does not adequately define the Earth's energy flows. Consider the Earth's thin atmosphere not as a blanket, or as something covering the Earth. It is an ocean of air that is part of the Earth. Put another way, it is an airy, moist mix closely coupled to the Earth's surface. The atmosphere is not forced to do this or that. It exists as a natural phenomenon that acts in its own way. Its swirling mix sometimes lets radiation pass through, sometimes it absorbs some of it, and mostly it scatters it. The atmosphere is a fluid system, like the ocean, but with its own unique blend of molecules and energy. It can raise balloons into the air and send them on their way. It can transform its energy into giant thunderstorms, sending heat up and down in violent ways. It is a system with varying density, but dense enough to cause an incoming meteor to burn up. It is a system with its own unique forms of energy. It produces lightning. It generates jets of electromagnetic energy. It creates different plasma, packets or fields of electrical energy and other types of radiation in the forms of pixies, elves, and sprites. Earth's atmosphere is a unique system that generates its own radiation signature. Treating it, or even thinking of it, as a greenhouse is counterproductive. Trying to model the atmosphere, let alone the climate, as a system that can predictably react to slight changes in trace gases has proven elusive. Even though global models have become more inclusive and sophisticated, with the publication of the fifth assessment, the IPCC reported that the models were unable to replicate the actual changes. Many climate researchers are increasingly recognizing the need to challenge the methods of research, the accuracy of the data sets, and the validity of the many assumptions that have been made. In 2016, the UN's World Climate Research Program launched the Radiative Forcing Model Intercomparison Project. Team members noted that radiative forcing has historically been uncertain, and that observational estimates of the forcing are also relatively uncertain. They described the potentially knotty relationships between forcing and response of the climate to it. They noted that the limited understanding of forcing has severely hampered progress in key areas of physical climate science. The IPCC is saying, in short, that radiative forcing may be the wrong approach, or in other words, the radiative forcing concept may have sent climate science in the wrong direction. The physics of the climate are unbelievably complex. Modeling them on a radiative forcing construct has led to frustration. We now have a better understanding of how and why a fresh approach to the atmospheric system is critical for the advancement of climate science.